Thank you for inviting me to this, and thank you for giving me the opportunity to talk about my work. Um, as Sagev said, right now I'm at Lawrence Berkeley, but I will just say that most of this work was done at Brookhaven National Lab while I was a postdoc there, with collaborators from Duke. And so what we were trying to do was we are all very excited for the next galactic supernova. I'll probably breeze through a lot of the background because I'm sure a lot of you already know it, and or I am preaching to the choir about how important this stuff is. Um, oh, sorry, one thing before I start, I can't really see hands or the chat. I am totally fine if people just interrupt me with questions or anything like that. Um, but so, with just some of the background, supernovae are some of the most common but kind of mysterious transients events. There's still a lot of questions regarding supernovae, from progenitor systems to how the explosions happen and the asymmetry in the explosions. The issue right now being that we haven't had a core club supernova in a very long time in the Milky Way for us to study. Right now, most of the information that we get is from supernova remnants that have exploded hundreds of thousands of years ago, as well as supernovae in other galaxies, but we can't really resolve those, and so there's still a lot of information that we aren't getting from those. And so, because supernovae are so important, and because we haven't had one in a very long time, we definitely don't want to miss the next one when it happens. And so, this paper is looking at how the Vera Rubin Observatory can work on that. And I just want to highlight a lot of the previous work that's already been done in the field. We built a lot from the Adams et al. Paper and the Walter et al. Paper. And then the Androni et al. Paper I will mention a little bit later in the presentation. One of the other exciting things about a supernova exploding, hopefully soon and now, is that we are entering a golden era of multi-messenger astronomy. And so we'll be able to get information on the neutrinos of the supernova with all the different neutrino observatories, as well as gravitational wave information potentially. And so, what we focus with this paper and with this work is on the neutrinos aspect. There's a couple of ways that we can work with neutrinos. The primary one that we're concerned about is using neutrinos as an early warning system so that we can point Rubin Observatory to the spot before the light reaches us. And so right here, I just have a plot from the Adams et al. Paper showing this idea of what the neutrinos would look like, the delay between the neutrino burst and what's called the shock breakout, where the light finally reaches Earth, as well as on the bottom plot that just shows the visual magnitudes. Um, and so with the neutrinos, we can get that location where the supernova is in a few different ways. The first would be like triangulation. I think actually I was looking at the previous seminar speakers. I think this was actually brought up last month, so I won't go too far into it. We are mostly interested in the observatories that can give us pointing information, which is right now Super K, and I think Juno will also be able to give us pointing information. I just don't know off the top of my head the status of whether or not they are currently running or still in the commissioning phase. There are also some papers showing that we could even get pre-supernova silicon burning up to a day before the supernova goes off. Um, I will say with that, it seems like that can happen from if the supernova is with 1 kiloparsec from us, which is pretty close, and we're trying to get the whole galaxy with this study. And so we will be working with pointing information. with the assumption that this is going to come from super K. And so this is where I get this number of 6 squared degrees at 10 kiloparsecs. So that will be like the pointing area if a supernova would go off at 10 kiloparsecs. And so you can imagine that area gets less the closer the supernova is and grows the further away it is. But luckily, there's also now a new optical observatory coming up that fits that pointing area really well. I'm sure you've all heard of the Vera Rubin Observatory. It's going to be great for trying to get the next galactic supernova for a number of reasons. First of which is a fast slew speed. This is an f 1.2 meter telescope. It's really compact. It can move really quickly and easily across the sky relative to other 8-meter class telescopes. And so once we get the alert, we can get on target fairly rapidly. It also offers a large wavelength coverage, which will be important later on, giving anywhere from like kind of the UV region to near IR. And lastly, the field of view matches pretty well with what we would expect from neutrino alert from Super K. We have large field of view of 9.6 square degrees, and so that overlays really well with the pointing given to us by Super K. And so what we're trying to do in this work is just see how great can the Vera Rubin Observatory be. And so we took a bunch of different models in order to model out how a supernova would look like in the galaxy. The first model I want to introduce is this trilegal model, which simulates the stellar formation and the stellar densities in the Milky Way. Specifically, I'll be just talking about there's kind of like a LSST edition where they put everything into LSST magnitudes and do the cutoffs and everything for us. And so you can see plotted here is the stars that we use from this LSST trilegal model. So you can already see that it has like the northern part of the Milky Way cut off. With this kind of LSST edition, there were two data sets. The first was single star evolution, which had 1.6 billion stars in it. And there was a binary system kind of evolution with the Milky Way. We want to keep it simple and just use the single star evolution. So kind of assuming that these supernova would just be single star progenitors, which there is a lot of recent research showing that that's not going to be the case, but we just want to keep it simple. So with those 1.6 billion stars, we made some cuts. The first being we just want to see what's in our galaxy. This trilegal includes the LMC or the SMC, but we didn't include that. We just want to worry about the galaxy and the pointing information that we would get from Super K from a supernova within our galaxy. The next cut was that we only wanted things with the initial zero-age main sequence solar mass of greater than 10. There's, again, studies that show that these core collapse supernovae can happen as low as 8 solar masses. However, we didn't want to worry about any weird physics happening with an electron capture supernova versus kind of the standard iron core collapse supernova. So we just cut it off at 10 solar masses. We did do a study of what happens if we included the 8 solar masses, and there wasn't that much difference in the final results, anyways. So with any simulation, you kind of want to test it against reality. And so we did a few tests to see just kind of sanity checks of how realistic and how good is trilegal as a model that we can use. So the first thing I would talk about is stellar distribution. So on the left is our probability maps of where you can find the stars. And so um, the top plot is just your normal probability distribution, and on the bottom is the cumulative probability. And so the first comparison was just Adams et al. 2013, already did something similar. Um, and you can see that we have kind of the same distributions, though our numbers are a little bit lower. But we have a peak at around 10 kiloparsecs, same with Adams et al. 2013. And so it matches with what's previously been done in the literature. One of the reasons I think that the probability is a little bit lower is that surprisingly, we went from about 1.6 billion stars to the total number of progenitor candidates after all those cuts I mentioned goes down to just a little under 40,000 stars, which is a 10 to the almost like 10 to the fifth or 10 to the sixth reduction, like 5 orders of magnitude reduction in the number of stars.
Hi, John.
And
Can I
so,
interrupt?
yeah, go for it.
40,000 progenitor candidates is actually more than I would expect. I think the estimate for the number of red supergiants in the Milky Way is more like less than 10,000. So how does this compare with catalogs of red supergiants, etc.?
That will be my next slide, kind of. I I think I might just actually skip ahead to that. I guess why I thought it was low was that I was looking at the saltpeter initial mass function, and it was something like the percentage of stars that you would expect falls to like 10 to the negative 3, like a 3 or only a 3 order of magnitude difference between like whatever your initial mass is. And so so I was expecting to get maybe like millions of stars with this simulation and not 40,000. So that's where that comes from. I will say there are other places in the literature which does support like this reduction. Um, and then with the red supergiants, most of the comparisons that we made were actually just to um, where the red supergiants are and how does that relate. And so I think this will kind of answer your question of our next sanity check. Like what percentage of core collapse supernovae are we actually like going to get? Um, and so we compared with Healy et al. 2024. Um, and what we did is, uh, unfortunately, it doesn't look like I have access to my cursor, but um, you can imagine we have this distribution here. I um, essentially just, it might be easier to look at the other one. I filled in kind of the gap and using similar stellar densities from trilegal. So essentially, what percentage of core cloud supernova candidates do we expect to be in the gap? And we only calculate to like 3% of the candidates should be in that northern gap. And so this is where I get that according to trilegal, Rubin should be able to get 97% of the progenitors. However, comparing with these red supergiants and the locations from Healy et al. 2024, Rubin's only going to be able to get about 57% of the red supergiant pool that Healy et al. Observed. And so it's probably more like the true value is probably in between those two. Um, just because there were some limitations with the Healy et al. 2024 paper of like magnitude cuts from using Gaia, where Rubin's going to be able to go a lot deeper, and so maybe could observe more of the red supergiant population than Gaia could. Um, and then also just they only looked at the red supergiant population. We'd be also interested in like wolf-rayets and other progenitor systems. So that was my comparison with the red supergiants. I'm not sure if that answered your question.
John,
I,
sorry, John, I have
yes.
a related question quick, but I want to help you move on. This is all just semantics, but one thing I wanted to be clear, you're using trilegal, but you said a version tailored for LSST.
Yeah, that's just to say that there are different versions of trilegal out. What I
Uh-huh.
mean specifically tailored to LSST is that it uses there it also in the catalog it has like Johnson filters, I think, but it also tailors like all the magnitudes for all of their stars to LSST magnitudes. It makes this kind of northern cut so where LSST can't
Okay,
observe
that's what
because
I
it's
wanted to be clear about. So this catalog that you're working with cuts out the stars inaccessible to Rubin, right?
exactly.
Okay, so that makes it more clear why you'd say 97% would be accessible. I mean,
Yes.
right? I mean, that's because there is something, but I want to be clear because we were discussing this in Journal Club. But ultimately, you had a discussion or you figured that the missing stars in the northern portion would be a small contributor, but maybe that's not the case.
Exactly. And so, I mean, you can see
Okay.
almost from these graphs that like it's a pretty uniform stellar density across. There's just like assumptions of the limbs and the arms have a certain stellar density, the bulge has a certain stellar density, and the halo has it.
Yeah.
And so it was kind of um, just taking that, I don't know, if you're looking at the plot with the galactic coordinates. It's just taking that right area and matching it with that missing area. And then how many stars do we think are in that kind of rightmost area? You get like 11,000. And so, or I
Yeah.
think closer to like 1,000. And so you get like the 97% that way.
Yeah. Anyway, no need to dwell on this. We could spend all day on trying to make the thing perfect, but let's see your results and try to do the actual follow-up, which are exciting.
Yeah. And so before we get into that, there's just one more
Oh, yes,
model that I want
yes,
to talk
yes.
about. And that is the simulated catalog of optical transients and correlated host or Scotch. So originally what this catalog was used for was simulating LSST, getting LSST like light curves and correlating it with host properties. What we ended up using this for is just taking those light curves. Again, it was just nice because they had all of the LSST magnitudes and the LSST, or sorry, it had all of the magnitudes and LSST bands. And so we just used that and primarily just to get peak magnitudes in LSST bands. Scotch does have a lot of models that you can use for your different supernovae. Um, to the right, I just show what we were able to get as absolute magnitudes with all the different models. And so we did try and do a split between type 2 supernovae and 1BC. And so the models that we used for the supernova 2 were just the templates, and the models for the 1BC, they just had a 1B template. And so what we'll be doing moving forward is assuming that there's a 70-30 split between a 70% chance essentially that the supernova will be a type 2, 30% chance that'll be a type 1 BC, and this was based off of observed rates from Liddell 2011. Um, the other thing that we do is trilegal does give extinction like AVs. However, they only max out to about 30 AVs. Um, and we were looking at other dust maps and we were noticing that potentially like near the center of the galaxy, the AVs could be up to like 200. And so instead of using the given AVs from Trilegal, we went with the extinction from the Schlegel et al. 1998 paper. We also used the corrections from the Shafley et al. I think it was like 2011 paper for our dust map. And so first, So starting to get into what can we actually see and what can we actually observe. I'll go in a little bit different order than we did in the paper, but first, first check. What are the odds that we can actually see the supernova just given where Vera Rubin is on the planet, and what are the odds that like we can like see it at night and things like that. And so for this, we took the trilegal star positions. We simulated 100,000 random like days and different times to test out a couple of scenarios. First one being, is it nighttime and can we just flew right to the target and see it right away? Or is it daytime, but it will rise later that night and we'll be able to, Rubin will be able to go on target later that night. And so here are the results from kind of those two studies. To me, they're not exactly surprising. You get for the available at night and focusing on that plot, all the red stars are going to be kind of your circumpolar stars, so they're always going to be available at night at some point. And then you can see the more north you get, the bluer it is, just based off of the time of the year. If it's winter or summer, you might not be able to get those stars ever. And so, and then for the available right away, it's kind of a mix between those, just based off of is it night or not. Um, so that gives us kind of an idea of what the fraction of stars are that we're going to be able to see in a just given time. And so now looking into, all right, let's assume it exploded at night and Rubin can see it. Um, our next study was just, okay, we're going to randomly assign either this candidate or pretender candidate will be a type 2 or it'll be a type 1BC. Um, and so could we see it with Rubin or like what's the given magnitude? And so on the right is kind of the money plot where it shows could we see it at peak magnitude or could we see again this kind of shock breakout effect? And to estimate the shock breakout, what we did was just did a 25% reduction, which is I'll admit pretty hand wavy because you would expect this was based off of Banovetz et al. 2016 paper where they looked at red supergiants and in the V band, which corresponds to LSST's R pretty well, um, they calculated that the SBO would be 25% of what the peak magnitude would be. So this corresponds to like 1.4 megs, which is why in the plot you kind of just see these shifts of about 1.4 megs between the shock breakout, the SBO, and the peak. I say this is a little hand wavy because this would be wavelength dependent. And so you would expect the difference between the two to be less in bluer bands and more in redder bands. However, at least with the redder bands, because they're able to see through all the dust and everything, I don't think it would actually affect it that much. And so you could maybe expect some better numbers from the bluer bands, but um, for this plot, I'm just plotting what the apparent magnitude is given the position and the dust and the whatever randomly assigned type it was. The vertical lines, the first one on your left is detector trip-off, which I will be mentioning a little bit later when we're talking about considerations for a procedure. Um, the first kind of group of dashed lines on the left is going to be your saturation limits for a 30-second exposure. And the solid ones on the right is going to be your 5 sigma depth for a 30-second exposure. So you can see that we do really well with 30 seconds for pretty much all of the redder bands. For the Y and Z, we're getting up to near 100% to like, I think it's 96% with the 30-second exposure. And it just gets worse, kind of the bluer that you get. But even with something like R, we would expect to get close to 80%. Um, we would be able to see 80% of the supernovae. Um, and then you just have to take into account that with the saturation, uh, there will be a large number that will also be just saturated.
Hi, John, can I interrupt again? What
Yep.
what's the basis for the 30 seconds? I mean, why can't you've got 100% control of this telescope. Why not just stare at it for like 5 minutes?
Um,
You're not trying to tile the whole sky.
so there, depending on with the location, there could be some tiling. I think the the neutrino pointing area, like let's say worst case scenario is at like 30-ish parsecs, then or sorry, not 30 parsecs, 30 kiloparsecs. You would have to do some tiling. Why not do it to 5 minutes? Is because we worry about saturating, we worry about missing the shock breakout. So the shock breakout can happen anywhere from seconds to days after the initial neutrino burst. And so you kind of want to play, it's one of the games is playing around with the exposure time to make sure that you can actually capture that sharp peak in the shock breakout. I would say it's saturation, as a shock breakout, as well as we are going to try and use the Rubin pipelines as much as possible. And I think at least right now, in the survey and the conditions, everything in the pipeline is set up for their nominal 30-second exposure. I'll mention a little bit later, it was one of the things mentioned in this Rubin TOO workshop of try your best to keep it to 30 seconds or 30 or 15 seconds because back then they're still considering the two 15-second snaps.
Okay, so
So
that's really the basis for the 30-second decision that you're using
yeah,
here to reuse as
yeah.
much of the Rubin infrastructure.
Rubin infrastructure. There is also worry about this kind of detector trip off if we would increase it to 5 minutes as well.
Okay.
John, that helped a lot. Maybe I'll ask more questions afterwards. But what about in the other direction? Like it's going to be bright. You could go down to 15 or like even a couple seconds. But I guess there's a whole parameter space of depending on how smothered in extinction it is and stuff. I don't know if you thought about those things.
So we initially were curious about like the 1 second.
Yeah. Yeah.
You can imagine, I don't think I have any um, plots with um, the this kind of dust map, but so pretty much everything shifts about 4 to 5 magnitudes to the left. In terms of your depth is going to be closer to 20 to 21, or sorry, it's like 21 to 22 for most of them. And then your saturation is going to be like 10 to 15. And so for the redder bands, you're still going to be able to get a lot of them. Um, for the bluer bands, you can kind of get a somewhat significant drop off in your ability to recover them. We did consider it. It is one of the considerations that we talk about a little bit later for the recommendations, is that I'll get into that a little bit later and we can talk
Sure.
more about it a little bit later. Um, But yeah, I think um are there any more questions on kind of like this plot? If not, the other consideration, now that we had like the SBO magnitudes was again, I mentioned it just now, you have this wide range of when the shock breakout can happen from seconds to days. And so what are the kind of odds that we can get the shock breakout? Um, and pretty much what we see, um, sorry, I should back up a little bit. So in determining this, the major thing between this and the other study we did with kind of the available right now or at night is that we put a random filter in place. So essentially, what are the odds that with the whatever filter we have in place, we can slew to the position and we can view the shock breakout. And this is the result where you can see the fraction of stars. Essentially, it's very extinction dependent, where you get anything kind of in these honestly like bluer than I or Z bands. And if you're unlucky enough to have one of those in, you're not going to catch the shock breakout if it's in the center of the galaxy. Um, and yeah, so this will kind of inform things later on in terms of like recommendations, um, which I'll talk about like what kind of things that we are considering going into this kind of six-step procedure that we end up writing in the paper. Um, the first being that we want to avoid saturation and tripping off the CCDs. We want to give the best localization that we can as soon as possible. Um, and so because one of the things that you would maybe consider is great, I get 100% of the supernova if I go to, I get 100% of the supernova and almost 100% of the shock breakout if I go to these redder bands like Z or Y. Um, there is also a caveat with Y in that it will only be in half the time. So let's say that you're working with like Z band. Z band will always be in. We can always just change the filter to Z band and go to our location, and we should be able to get the supernova. However, when you get to the redder and redder magnitudes, you have also a higher percent chance of tripping off your detector, which the way that the LCD camera and Rubin is set up is you'll actually trip off three of the CCDs if you would do a detector trip off. So you can kind of see here with the table in the Z band, you'll get 100 you should be able to get light from 100% of your supernovae. However, 14% of those could potentially trip off your detector. It will take minutes. I think that it's down to like 5 to 10 minutes to get the detectors back up. But again, when you're worried about the shock breakout, you want to minimize any downtime that you have because you don't know when it's going to happen and the time range is huge. And so to avoid kind of these conditions of saturation or tripping off the detectors, considerations would be like shortening the exposure time, as well as possibly changing the filter. I would say both of these, you're essentially just one of the considerations is you're looking at where in the galaxy did the supernova go off. So to go back to the previous slide, so if you're looking at this plot, if our localization is somewhere to, I don't know, the right side of this plot, you're pretty safe shortening exposure times, possibly changing filters, though again, um, that's a changing filters takes about 90 to 120 seconds. And so there's a little bit of hesitancy if we're looking for the SBO to do that. Um, But if you know that if it's off the galaxy center, you could shorten the exposure time, and you could also maybe change the filter. Um, just another consideration would be that we want a system set up to filter out any known transient objects if we're trying to take images and we know of variable stars, we know of asteroids, we want to be able to filter those out efficiently when we're looking for the supernova. And the other question that depending on when the supernova goes off, would we have access to templates? Um, Essentially, if we're into year 3 or 5 of the survey, we most likely will have templates or at least something of the galaxy. But if it happens sooner rather than later, we need to consider what do we do if we don't have access to templates? How are we going to subtract everything, try and do subtraction like a credit field and all of this stuff. So this is the proposed strategy. I'll go over it quickly. I just copy and pasted what we had in the paper. Essentially to get the shock breakout, as soon as a neutrino alert is triggered, move to the target area, start taking your 30-second exposures with whatever filter you have. And then depending on if you have templates or not, take multiple exposures to be able to perform on-the-fly difference imaging. Um, and again, depending on the distance of the supernova, there might be some tiling that needs to be done. So tile over the entire region with multiple exposures. Also, good idea in general to make sure that you're not getting any weird sensor effects or anything like that that you could mistake for a supernova. Um, and then there's a few things that we leave ambiguous to like the Rubin TO committee of after a determined times change to either the Z or the Y filter so that we can get the rudder filters to check to make sure that we're actually going to get the supernova. Um, then you just cross-check it with any known objects in the sky. And then essentially, step 5 is try to start building the light curve. And does the light curve look like something that we would expect from a supernova? Um, and then one of the things that kind of was discussed in the workshop was, which I think I actually talk about, yeah, the next slide, but um, we went to this Rubin TOO workshop in 2024, and one of the big issues there, I mean, there were gravitational wave people. We were one of a few neutrino people. Um, was how long do you stay in this kind of TOO program? Do you find the candidate and immediately just give a GCN circulation and then Rubin will stop observing because other observatories can see it? Um, do we try and get a full light curve? In this paper, we kind of advocate for getting as full of a light curve as we can just for cross calibration with other observatories. Um, and so kind of going into what LSST has done with TOs so far, as I mentioned, there's this TOO workshop, which was the findings and kind of the proceedings of the workshop got put into this Androni et al. 2024 paper. Um, right now, there's a graduate student out of Zurich, Sean McBride, who's working on getting the TOO infrastructure set up. He was monumental in getting these two kind of gravitational wave related GCNs released last year, um, and integrating these schema alerts. And I think he's planning on going to the SPIE meeting and talking about what they've done so far. So I guess stay tuned for that paper and those results. Um, which brings me to my last slide. So just brief summary, we were using trilegal and Scotch to see whether or not Vera Rubin Observatory will be likely to observe the next galactic supernova. We found that it it should be able to observe pretty much all um, the supernovae, at least at uh, peak magnitude. And we also have a good chance, depending on the filters and such, and the type of progenitor, we have a good chance of observing the shock breakout as well. Future work, Claire, at least Hébert at BNL, is working on kind of these crowded field core collapse supernova identification strategies using the Rubin pipeline so that we can get this, we can identify the supernova candidate as soon as possible and bring it, get it out to the community. And then just general work of starting to ingest the alerts into the Vera Rubin LSST infrastructure. Um, so that's all I had. Thank you again so much for letting me talk about my work. Um, I'm happy to take any questions.
I'll ask a question right now. I got lots. John, thanks so much for this. It's very helpful and clarifying aspects of the paper. This last part, the core collapse identification. So in my mind, I could see how crazy it would be to identify the emerging supernova from all the chatter of the other alerts that are coming through. There'll be obvious cases, of course, but there'll also be a non-negligible number of where it's not as easy to discriminate the rising supernova from, all the variable stars and such that are in the field. Is that what this person at BNL is doing, or am I thinking something different?
Um, there are some aspects that she is working on. There are some differences. So, like right now, there's a big thing at for these alerts for Vera Rubin and LSST on kind of their side of pre-identifying, like, oh, this is a known asteroid because we can chart the path. Oh, this is a known variable star. So there's a little bit of filtering that we're kind of
Uh-huh.
assuming is going to happen at the LSST side. Um, and then what she's primarily doing is right now working on like source injection of we expect like let's say a supernova happens here in a crowded field and studying are the subtraction methods even like um, can we set up the algorithm for this on-the-fly differencing so that we can get this kind of injected source and kind of at what magnitudes can we start to expect to see the supernova candidates, as well as I think she's going to start to look into how well does the template subtraction work and how much noise are we getting out of that and things.
Yeah, that's exciting. I'd be curious to know how, with what success rate that you can retrieve a variety of the different types of supernova explosions, especially given my bet that the next one is let probably a 1A. But if it is a core collapse after that, then it's going to be on the other side of the galaxy, smothered in extinction.
Yeah, and so you have the smothered in extinction, and then I mean that will happen most likely at the center of the galaxy, and so you're going to have an incredibly crowded field as well. And
Yeah.
so this is what luckily she gets to worry about that and how to deal with that for at least for now. Um, because yeah, it's a tough project to be able to like match PSFs and do a proper subtraction and everything.
Yeah. And let others go, but I really want to applaud you for the work here. The Having thought about this for some amount of time, there's just such a broad range of parameter space where it could be so bright it saturates to so faint you can barely detect it, right? And all the different
Yeah.
explosion scenarios. So it's very hard to be able to be prepared for everything.
Yeah, and I think that was, I mean, if I was given the time and the money, I would love to go into like the binary systems and how would those look in difference. And there was a few assumptions that would be fun to go into. But as you said, like the parameter space is huge. It would be kind of a monumental effort to try and predict anything and everything that could happen.
Yeah. Jim, you got your hand up. Why don't you go ahead?
Yeah, I had a question. So John, how fast, or maybe you know, maybe you don't know, how fast could the difference imaging actually be done? How quickly could you compare two images and say, "Oh, I found the supernova"?
Um, so the numbers that I know of off the top of my head would be like the LSST alert production. Um, you right now, I think they're actually beating specs, and within 2 minutes, you can get an alert
Okay.
from when the shutter closed. So be about, I would imagine, a minute or two to run it through the pipelines. And I also imagine that if this was happening, we would hopefully get more resources in order to process things faster.
Other questions? Danny, it might be you if you have more.
Nah, I won't pepper them anymore. John, there'll be a follow-up after this. This is exactly the kind of talks we need. And it's, I only learned that you guys were doing so much after the paper cropped up. So there's a lot of overlap in interests, especially now that SNEWS 2.0 infrastructure is coming up online and stuff. Things that we know we got to do. We just have to get around to it. So it's a good moment now to really think together.
Yeah, I agree.
We keep saying we want the next galactic supernova, just not today or tomorrow.
Exactly.
Maybe a
Yeah,
year from now. And I say that every year.
there's a little bit of that on this side of let's hope it doesn't happen during year one of
That's
LSST.
right.
Let's hope it happens in year nine or something.
Okay, well, if there's no further questions, let's all thank John again for a great talk. And John, thanks for letting us know what Rubin is up to with this.
Yeah, no, again, thank you so much for letting me talk here and being able to discuss my work.